everyone. Today we are going to be learning about voltaic cells. So just so you're aware, voltaic cells are also called galvanic cells, so they'll be used interchangeably throughout the unit. Voltaic cells run off of redox reactions to create electricity. So in order for the electricity to be transferred, we need to have passing of electrons, which is what redox reactions are. A battery is a prime example of what a voltaic cell is that we use every single day. So let's go through what are the basic components of a voltaic cell. Here I have set up what's going to be our voltaic cell. So the first thing you need to start with are 2 beakers of water. So in those beakers of water, we are going to be dissolving zinc sulfate into one, and we are going to be dissolving copper sulfate into the other one. So keep in mind that when you dissolve these compounds into the water, they are going to break down into their ions. That means that in the one beaker, we will have zinc ions, and zinc's ions have a charge of 2 positive. And in the other beaker, we will have copper 2 positive. So here are our coppers. The sulfates we will look at a little bit more depth later, but right now we're going to leave it out so it's a little bit simpler. So we have our ions in there. The next thing we need, which I already have here, are electrodes. So on the left we have a zinc electrode, which is a piece of zinc metal. And on the right we have our copper electrode, which is just a piece of copper metal. So the last thing we need to have a functional voltaic cell is a piece of wire that connects the 2 electrodes. So crazy thing happens. As soon as I connect my wire from my zinc electrode to my copper electrode, electrons are actually going to start flowing through the wire. And that is because it's a spontaneous reaction. And we have a redox reaction where electrons are being transferred. So the only part that I am leaving out right now is the salt bridge, and we'll take a deeper look at the salt bridge at the end. But right now, for simplicity, we're going to leave it out. So we've already went over that moving electrons is what creates electricity. So that means that there needs to be some kind of electron transfer happening here. So we have our beakers full of solutions. We have our piece of zinc metal and a piece of copper metal. And like I said, we'll deal with the sulfates later. So we need to figure out, why do electrons start moving between the 2 metals? And the reason for this is that the 2 different cells are actually playing a bit of tug-of-war for the electrons. So our zinc solid has a very weak pull for electrons. That means it's really willing to let go of electrons, whereas this copper 2 positive, this copper has a strong pull of electrons. It really wants electrons. So within there, we have our copper 2 positive being our strongest oxidizing agent, which means it wants electrons, and zinc here being our strongest reducing agent, which means it wants to lose electrons. So keep in mind that this reaction is spontaneous because the SOA, zinc, is above copper 2 positive on our table in our data booklet. So what's going to happen is the zinc here is going to, because it has a weak pull of electrons, it's going to give away electrons. So the electrons here are going to be transported along the wire. As we lose electrons, we change our charge on our neutral atom to be +2. So neutral atoms exist as metals, whereas as soon as it becomes an ion, it tends to dissolve in the water. So as it loses the electrons, it becomes dissolved in water, and our electrons travel along this wire all the way to the other electrode. And in this case, remember we said that the copper 2 positive has a very strong pull for electrons. So the copper 2 positive is like, oh yeah, I need those electrons, meets up with the electrons, and then as it gains electrons, it changes to copper solid. And like I said before, if it changes to a neutral atom, it becomes a metal. So copper is going to attach onto the electrode here and now be a full metal. So let's go through that one more time and think about where the gaining and losing of electrons is going on. So zinc is going to be losing electrons. It wants to give away its electrons. When it does that, the electrons are transported through the wire, and the zinc changes from zinc metal to zinc 2 positive because it gave away those electrons. Copper 2 positive over here has a very strong affinity for the electrons, so it's going to come up, meet up with the electrons, and it changes from copper 2 positive to copper solid. So as you can see, the electrons, they travel this way through the wire. They're going to travel from the zinc solution to the copper solution. So as we are going through this, you can see that the zinc is going to keep dissolving in solution while the copper is going to be turning into solid. So over time, you can see that your zinc electrode is going to start wearing away, getting smaller, while your copper electrode gets bigger. So this is going to keep happening until your battery is completely wasted away because there's no more zinc left. So that's exactly what happens why batteries die. It's because all of your one electrode are completely used up and you only have your copper electrode left. So if we go back to what's happening to our electrons, remember the zinc changes to zinc 2 positive and it loses those electrons over to copper 2 positive who gains them. So one more time, zinc loses electrons, and remember that losing electrons means that you're undergoing oxidation while your copper is gaining electrons. So you have copper undergoing reduction and zinc undergoing oxidation. So we call this piece of zinc metal the anode because it loses electrons, and your copper metal the cathode. So remember your mnemonic devices at this point. Leo says Gur, loss of electrons is oxidation, gaining electrons is reduction, and then of course red cat, which means reduction at the cathode, and anox, which means your oxidation occurs at the anode. So those will become very useful to you. So let's also have a peek at the the half reactions going on. Your zinc starts as a metal, and then it loses 2 electrons to become a zinc ion. So here's your half reaction. Your zinc solid gets broken down into the zinc ions and it transports 2 electrons. It loses those 2 electrons. Your copper, on the other hand, remember it started as an ion in our solution, and then it gained 2 electrons and became copper solid. So here are our 2 half reactions that are going on. One is gaining electrons while the other is losing electrons. So these are half reactions because they show half of what is going on in our cell. When we put these together, we have the full story, and we can see that our electrons would cancel out and we would be left with our full equation, which is zinc solid plus copper 2 positive yields zinc 2 positive and copper solid. So there's our overall reaction. One of the last things we're going to touch on is cell notation. So when you're doing cell notation for Voltaic cells, on the left-hand side, you are going to be putting the oxidation, which is what happens at the anode. And on the right-hand side, you're going to be putting reduction, which is what happens at the cathode. So at our anode, we had zinc solid changing to zinc 2 positive. So that is the first part of our cell notation, zinc solid changing to zinc 2 positive. The double line in the middle represents the physical boundary we have between the cells. And then on this side, we had copper 2 positive changing to copper solid. Keep in mind here that your zinc is going, as it has the weak pull for electrons, that is going to be your strongest reducing agent, and your copper 2 positive, that is your strongest oxidizing agent because it has a strong pull for electrons. Okay, so I think that it's time to look at our salt bridge, as I promised at the beginning of the video. So here I have a salt bridge that I'm going to add in. So the salt bridge is simply a connection between the two cells, and it is literally that. It's a bridge between the two cells that contains some kind of salt. So salt, as you know, is NaCl. So sorry, just fitting these in here. So in solution, it breaks down to Na positive and Cl negative. So remember that at the beginning I told you that the sulfate was in here, but we haven't added it yet. So now at this point I'm going to add it. So we have sulfate here and sulfate on this side. So as you can see, when this reaction continues to take place, we are going to have more of our zinc solid changing into zinc 2 positive, and on this side, all of our positive, so remember there's copper 2 positive in here, is going to become solid here. So here there is a buildup of negative charge, and here overall there's still going to be a buildup of positive charge because all of those zincs are going to be dissolved into water. So here's another one that could dissolve into water as your zinc solid disappears. So we have a buildup of negative charge here and a buildup of positive charge here. So the salt bridge works to balance the charges. As we have negative charge over here, positive sodiums are going to be released from the salt bridge. And I forgot to mention, the salt bridge has cotton plugs on the end so that the ions can't flow freely through. But they can slowly leak out to balance the charges. So Na positive is slowly going to leak out into this beaker to balance the charges. And then as you can see, the positive charges over here, we're going to have Cl slowly leak out to balance the charges. If the charge becomes too negative or positive, our battery won't run. So that's the purpose of a salt bridge. And eventually these Cls would all transport into this, and this sodium would transport into this side to balance out the charges. So there you have it. We have a summary of a voltaic cell. I guess they're pretty important if they charge our phones. So keep that in mind and hope this helps.